understand how brittle these methods are. So as physicists who are often putting these methods kind of into practice, what are the approaches that you take to kind of make sure you're not shooting yourselves in the foot using kind of very complicated, let's say, mathematical forms like these deep neural networks, where we often don't quite know what their properties are on out of sample? And does that worry you? Do you lie awake at night worrying about this? Or do you just test them? You're like, it works good enough. Like, we have bigger fish to fry.
Yeah, so actually we worry about that a huge amount of time. And so in fact, when we do physics analyses with machine learning, they take much longer than the simpler ones because we spend an extensive amount of time on validation. One of the things we're worried about is actually bias. And we've certainly seen examples of this where you use some fancy technique and it does very well, has excellent performance, and gives you a very accurate but completely wrong result. So that's one example along the lines that you have. So actually what we try to do, and of course we'd welcome more techniques to do it, is to actually understand what it's doing. So for example, like we're using kinematic information about particles. So we will actually be looking to see what precisely it's selecting on to understand that. Also to understand whether the correlations that we see in our simulation is reproduced in the data. And so we spend upwards sort of a year typically in the sort of level of validation. So yeah, we worry about it a lot.
Yes, I'd like to add to this. So from our perspective in my work, we're studying a quantum field theory, and we want to retain the rigor of the fact that we're studying a well-defined quantum field theory. So we don't use machine learning for many places where it might be convenient, but only in places where you can prove that even if the answers are wrong, you're still maintaining the rigor of a quantum field theory. And so it just, if it's wrong, it will make things slow, but never can make it incorrect. And so we go to great lengths to prove that.
So I have many experience to tune the hyperparameters of the neural networks, particularly its width, its depth for the neural networks. So in my mind, I think there are at least 3 elements that will determine if machine learning will work or not. The first element is the quality of the data set, right? So if your data set is contaminated by a large amount of noise, it's difficult to make machine learning work, right? So you have to first pre-process your data set and to kick out the outliers to make your machine learning model more robust. Okay, the second element is in the theoretical part that. For example, if you're gonna solve an inverse problem, right? You're gonna identify some parameters of the equations. The first thing you have to know is the well-postedness of the inverse problem, right? So if you use machine learning, if you have to make neural networks, you have to make the machine learning model to feel the well-postedness of the problem. So you have to add enough constraints to the loss function of the neural net models. So that's the baseline. You have to carefully select enough constraints. Okay, and the third element I think is the tricky part. That is, you have to tune many hyperparameters, right? For example, in physics-informed neural networks, in the loss function, if you consider a system of equations, right? You have to put a lot of terms in the loss function, right? So we have to carefully tune the weight coefficients before each term. So that's the most tricky part. Yeah, for the other parts, like how to select the activation function, how to do the uncertainty quantification, sort of something like that. It's quite complicated.
So a question for Professor Shanahan and Selyak. A question about these very high-dimensional spaces, so 10 to 12 dimensions, or high dimensions of the full dark matter distribution in space. If we divide out by the gauge group, we will, of course, reduce dimension. But do we know that that now the resulting support of the interesting support of the distribution is a low-dimensional manifold, and can we estimate the dimension of that manifold? In other words, the dimension of the latent space as a manifold rather than a linear space, can it be estimated?
For our cosmology applications, it's essentially given by the noise. Basically, noise destroys information, and at some point you just don't need that latent space because you know that there's nothing there. And when you do this kind of, for example, map reconstructions, you are driven to a solution which is zero, right? In other words, prior defines it. So you are actually you do get the answer to that question explicitly.
Yeah, so in our case, this is, I mean, it's somewhat of a tricky question because an optimal autoencoder would send you back to your set of random seeds that you could have used to generate the configuration in the first place and the handful of real parameters that define the action of your theory. But that's not a practical dimension of a latent space, you know, your 5 random seeds. So the practical dimension is much harder to work out.
Thank you for the talk. I have a question for the last speaker. So how do you enforce injectivity for your generative model, and why does that matters? Thank you.
Yes. So first of all, how do we enforce injectivity? By having lower dimensional latent space, orthogonal transformation that uplifts from low dimensionality to high dimensionality, and then the rest is bijective. Okay, and then why does it help? It helps because in this posterior type of analysis that I was showing, an injective mapping minimizes the number of multiple peaks. Okay, you only have multiple peaks because if the data really are consistent with multiple solutions, and otherwise you'll just get a single peak in the posterior analysis. When you don't enforce injectivity, then you may have several multiple peaks in the latent space just because your mapping did not enforce injectivity.
Thanks. So I really like the hardware talk. I was wondering, beyond latency and obviously things like accuracy, is there something else at predict time that's important? I was thinking about sort of energy budget or costs, and how are you thinking about sort of even beyond the FPGA ASIC world? Is there another generation of chipsets that you think may be useful?
Yeah, so of course the latency is one measure. Maybe I went through that one slide too fast about, the data throughput. So you can actually, in the most optimal way, you can run your algorithms. Ultimately, you care about how much data you can process. So that's definitely one measure. Energy is one concern. FPGA is pretty efficient, but if you have like algorithm, you design an ASIC specifically for that, it's going to be more efficient, but then you have to invest money in terms of engineering power, etc. So it depends on the application. It's hard to say which one is more cost effective. And of course, for all these services, as a user, you want to know how things scale up and how much support you have, and also in combination of, whether you can get funding support in terms of whether to purchase hardware. So it gets really complicated to optimize for everything, but it has to be application specific.
Questions from the audience?
Sorry. We're actually doing some work with the AWS and also with TPUs as well. So for TPU, we can actually accelerate training as well, which probably many people are more interested in that aspect. So, yeah.
Hi, thank you. I have a question on stability. I guess my experience with these different machine learning models for physics, stability seems to come up a lot. That can definitely be a challenge. So I guess my question was, what sort of techniques have you found for like nonlinear systems?
Well, good question. So, I mean, in general, well, you can first ask, I mean, there are many notions of stability, right? Depends in which domain you go. So here, right, we focus on dynamical system, and they are kind of viewing the problems through the Lyapunov stability lens is natural. And so basically you could we hope that we can extend this to nonlinear systems by just look to the Jacobian and then do some eigenanalysis on this. So if there are ways to extend it. There are also like other ways to do it, like, so here I proposed a prior, but you could also project it on the nearest stable matrix, forms like that, we look into it. But in general, the caveat is that some of those techniques are have some numerical issues, so you have to really carefully implement it to solve them. So with Lyapunov, what we do probably next is look to formulate it as a semi-definite program, which might be neat, because they're like the solution to P is not unique. So there might be good or bad solutions, so you have to be a little bit careful how to select this. But yeah, so we just started to work on this, so maybe I can give you a better answer in a year from now or so if there's some more work done, or I'm happy to talk more offline.
Any other questions? We technically have a couple of minutes. Of course.
So it's actually a question for you mostly, but a more general question. One can think of physics as ODE and PDE systems. One can think of them as a deep network as well. And in that case, what does one gain by developing a different network rather than use the original one, which one would think is actually the optimal one? For example, we can certainly develop the backpropagation and stuff like that through ODEs and PDEs, and in other words, we can do everything that neural networks do. So what's the gain? What's there to be gained by using neural networks rather than physics-based neural networks, which are ODEs and PDEs?
So you're asking what's the advantage of? Sorry, I think I missed your point. So your point is
the forward models are, you can think of them as a deep network of ODE and PDEs.
Yep.
And therefore it is already a neural network. Why do you want to rewrite that into a different neural network? What do you gain by doing that? When do you gain and when do you not gain?
Okay, so think okay, so I think you're asking why I put a neural network into a governing equations, right? Why I put the PD residue in the loss function. So I think so our main objective is to solve the inverse problem by using deep neural network, right? So we want to we want to put the parameters to be identified in the loss function of the neural network. In this way, it could be very efficient to solve the inverse problem, because conventionally we solve the inverse problem by solving forward problem many times, right? If we use neural network, we can solve the inverse problem one time. So that could be beneficial in terms of computational cost. So am I answer your question?
Okay, so if you do it many times, then it's advantageous. If you only do it once, then you agree it's not.
If I only do one time, that will be faster.
It will be faster using physics-based.
So, yep.
What we want to do is solve it only once. So for example, we can make the cosmological parameters input to a network, and then we rely on the network's ability to interpolate between different cosmological parameter value samples and solve for the evolution as a function of space and time and parameters. And then we have a global solution across over the entire parameter space. So it's a single training.
Okay, maybe just another comment on that. I know a lot of stuff was more focused on, well, let's say if you're coming from an experimental side and you have a simulation for the detector, the forward direction is not necessarily going to be differential in the backward process, and that's something where this can really help. Just to give another example where it really is needed.
So since we have a pretty tight schedule, I will encourage the rest of the conversations to continue over lunch. I'd like to thank all of our session speakers.